So this is our lecture on more chemical reactions, and specifically we're going to be talking about acid, base, and precipitation reactions. And so far we've already talked about oxidation reduction, so that's one of our major types, but then acid, base, and precipitation reactions. These two different types of reactions both follow this general format here, and this is going to make more sense when I give you a couple examples. But they're going to look a little bit like this. Sylvia's got a question. We'll get to it in just a minute, okay? We're just introducing that now. So you'll have a compound which consists of two things, a compound which consists of two things, and then they're just going to like swap partners. The technical term for this is a double displacement reaction. I'm not going to test you on that, but you can see why they call it that. It's almost like, oh, hang on, we don't need a period there. It's almost as though you had two couples that went on a double date and then they went home with the other person's partner, is basically what's happening there. And of course, the order there is not trivial. These are ionic type compounds. In fact, I'll put that over here. And because they are ionic compounds, you have the cation is always listed before the anion. So this cation is not going to react with that cation because they both have the same charge. Instead, this cation is going to associate with that anion because they have opposite charges. And then that means that this cation is going to interact with that anion, but because the cation is always listed first, that's why the C comes before the B, if that makes sense. So your outside ions are going to form a new compound, and your inside ions are going to form a new compound. So, precipitation reaction occurs when two ions form a substance that is not soluble. Let's see, two ions in solution form a substance that is not soluble in water. So what happens is that you have these two solutions and you mix them together, and then all of a sudden this solid will form in what used to be just a clear solution. The solid will form and fall to the bottom because that solid is not soluble. So precipitation, you can think of precipitation like rain coming out of the sky. That's another word for precipitation. But if you were in that solution, you would see, and it would feel like there was this tiny solid particles falling out of the solution in kind of the same way, all right? So here are a couple, here's one example of a precipitation reaction here. Now, in order to indicate that there is something that happened in terms of the phase, that is something that was previously dissolved is now solid falling out of solution, we have to include these we call these phases. So now not only are we going to include our reagents, but we're going to include the phases. And the phases are like this. They're always in parentheses. S means solid, L means liquid, G means gas, and then you see this AQ means aqueous, which means dissolved in water. And we did say that often you'll find ionic compounds dissolve in water. Of course, when they do dissolve in water, they dissociate, right? So these actually are disassociated ions, one from another. Now they're all running around happily in this solution and running around happily in this solution until you put the two together. And then what happens is that whenever the barium ion encounters the sulfate ion, they say, whoa, I'm way more attracted to you than I am to the water. So I'm going to cling together and fall down to the bottom. If we could draw a little picture of this, you would see you've got like a little beaker, and you take one solution, you add it to another, and then you're going to form tiny solid pieces that fall out onto the bottom. Does this make sense? Are you guys with me so far? Note in this example that the barium from the first compound came together with the sulfate from the second one, and the sodium from the second one, came together with the nitrate from the first one. And then when you make those new formulas, they're based on the charges and not on the numbers you have here. So for instance, you have 2 nitrates here, but you don't put NO3 on this side. All right, this is very important. You have 2 nitrates here because the barium is +2 charged and the nitrate is -1 charged. So you have to have 2 to balance it. But as soon as you're pairing it with sodium instead, because it's +1, then I only need 1 of each. And then you can accommodate this by putting in a coefficient, right? But it's very tempting. Students will often just translate this 2 over and say, well, the middle ones go together, so I guess I'm making Na2 NO3 and that's a terrible idea. Don't do that. That's completely wrong, right? Instead, when we combine the outsides and the insides, we should always make a note of the charge. If barium is +2 and sulfate is -2, I'll need 1 of each. And if nitrate is -1 and sodium is +1, then I will need 1 of each. And after I have appropriately made my neutral ionic compounds, then I can balance it. Does everybody get that piece? And then, yeah, so Sylvia's question was, is this what we're looking for? And that's the answer. Because I made a solid where previously there was not one. Previously everything was dissolved in water and now there is a solid. That tells you that this is a precipitation reaction. Because there's that little solid there. Good question. All right, so the question that you guys should have is, well, how do I know if something is going to be solid or not? Right? Usually, so far, all of the ionic compounds we've seen were like, okay, they'll probably dissolve in water, but how would you even know? And to answer that, I'm going to give you a table of solubility. This is my solubility table, and you are going to memorize this for the test and for your lives. Okay. Solubility rules. And actually, as it turns out, most ionic compounds are not soluble. If they are soluble, they do dissociate and form electrolytes, but most of them are not actually soluble. And as an example, basically all of your rocks can be classified as ionic type compounds typically. All your minerals, ionic type compounds. So this is our rule. This is our solubility rules. These are the things which are soluble. And basically, if it's not on the table, then we just say, okay, that's just not going to be soluble because it's not on my table. So here's how you're going to read that table. You're going to say, if I have a group 1 ion in my compound, for instance, hydrogen, sodium, lithium, potassium, then I will be soluble, because this is a table of things that are soluble, and there are no exceptions. So sodium sulfate, we predict will be soluble because it has a sodium in it. And I don't have to go any further than that. Sodium nitrate, I predict will be soluble because it has a sodium in it. I don't have to keep looking, okay? These polyatomic ions, ammonium, nitrate, acetate, and perchlorate, are, again, always soluble with no exceptions. So the barium nitrate is soluble because it has a nitrate in there. Because as a nitrate, it's definitely soluble. We don't have to look any further. Sodium nitrate, we already determined was soluble because it had a sodium, but if it didn't have a sodium, well, it has a nitrate, and that would also make it definitely soluble. No exceptions there. These halides, chlorine, bromine, and iodide, chloride, bromide, iodide, these are considered to be very soluble, almost always soluble. These are the only exceptions, the only circumstances in which you would say that these ions would not be soluble. So if I have chloride with magnesium, you'd say, yep, that's soluble. But if I have chloride with silver, you'd say, no, that's not soluble. Right? And finally here, sulfates. Sulfates also tend to be quite soluble with only these exceptions. Note that those last two are the same, but silver is kind of like a special weakness for the halides. Barium and strontium are special weakness for the sulfate here. If it's not on the list, then it's not soluble at all, we predict. Now, your textbook might have a slightly expanded set of rules, or it might look at it from a slightly different angle. For the purposes of the test and keeping things very simple, this is what I will test you on. I'm not going to test you on anything else or any other weird, crazy exceptions, okay? So we can trust this one to help us predict what's going to be soluble or not. So if we go to our worksheet here, whoops, and we just have this little section here that says, let's just predict. Let's make sure we understand this table. We do need to memorize this, but hopefully it should be pretty simple because it's kind of groups things together. You don't have to memorize each of these individuals. You just say group 1 ions. All right, so let's look at this. Li2S, would you predict that that would be soluble or not soluble? Soluble. Why soluble? Good. It's got lithium. Lithium's a group 1 ion. Group 1 ions are always soluble with no exceptions, so lithium sulfide would definitely be soluble. What about iron 2 hydroxide? Soluble or insoluble? Insoluble. Perfect. Now the reason that this one is insoluble is because neither the iron ion nor the hydroxide ion are listed in a list of things that are soluble. So since neither the iron or the hydroxide are listed, we can presume then that it would just not be soluble. Good. What about sodium carbonate? Soluble. Excellent. Good. Again, because it has sodium, then we don't even worry about the carbonate because it has sodium. The whole thing's going to be soluble without exception. All right, what about potassium hydroxide? Soluble, yes. Why? Because it's got potassium. Potassium's a group 1 ion, always soluble. Excellent. PbCl2, soluble or insoluble? Insoluble. Good. PbCl2. Why is PbCl2 insoluble? Because lead with chlorine specifically is an exception to the things that are soluble, right? Because chlorine's usually soluble, but lead is one exception to that. All right, hang on. Zach wants to go back to FeOH2. Why is this one insoluble again? Nothing's on the table, right? This is a list of all of the things that we can presume to be soluble. So if it's not on the table, then we assume it's not soluble. Does that make sense, Zach? Awesome. Okay. AgI, what do you think? Insoluble, why? Yeah, because silver is an exception to the rule where chlorine is usually soluble. Okay, chromium carbonate, chromium 3 carbonate. Insoluble. Why? That's right. Nothing on the table. Neither chromium nor carbonate are on the table. Okay. What about AgCl4? ClO4. Soluble. Why? Yeah, the ClO4 right here is one of our things which is always soluble, right? So careful, you might, if you looked at that as AgCl, you might think that it's an exception, but it's not Cl, it's ClO4. Okay, good. What about the copper 2 sulfide here? Insoluble. Good. And finally, barium sulfate. Insoluble. Why is barium sulfate not soluble? Because barium is a specific exception to the sulfate. Oh, I skipped. Why is the copper sulfide not soluble? Neither of those are on the table. Good. All right. Do you feel like you've got a pretty good understanding of what this is like? It is a little bit simpler when you've got the table in front of you than it is when you're sitting at the test and you're trying to remember it. So this is definitely one of those places where you memorize it, and then before you even take the test, after you've like checked in and you're on the test, you can just sit down and write it out to help you remember each of those. Okay. All right. So the next thing we want to do with precipitation reactions is to predict the products of a precipitation reaction. Really predict the products of reactions of this type in general. So here we go. We've got this equation. And we need to predict what's it going to form and is there going to be a precipitate? That's what we want to be able to do. So, what did I tell you? What should we do with this? First thing we should do. Oh, good. Sarah's a little bit ahead of us. We're going to combine those outside ions, right? And we're going to combine the inside ions. And it will behoove us to check our charges because we want to make sure they cancel. So silver is +1 here, nitrate's -1, +1, -1. Okay, so I gave you an easy one to start. And so we can predict that our products are, whoops, here we go. A little bit bigger. The silver with the chlorine. We don't know what that phase is yet. And the sodium with the nitrate. And we don't know what that phase is yet, right? And then, once we have predicted the products based on the charges, we can look up at our chart and say, okay, would that silver chloride be soluble or insoluble? What do we put in these brackets? It's going to be solid. Good. What about the NaNO3? Is that going to be solid or is it still aqueous? AQ. Perfect. Perfect. How did you know that the silver chloride was going to be a solid? Right, because the chloride, when paired with silver, is an exception to things that are typically soluble. Excellent. How did you know that the sodium nitrate was going to be soluble? Right, sodium is always soluble, so you're good on that. Okay. All right. Well, that's good. That was a really great start. Okay, this is what we call complete molecular equation. Because here I have my chemical reaction. It's given as an equation. Form this goes to form that. And I'm showing everything here as a complete molecule. But in solution, if I'm an ionic compound and I'm soluble, am I present as individual molecules? Oh, can you hear me now? Okay. They're not present as individual molecules, right? We have essentially a little beaker here, and it's got water, because that's what it means to be aqueous. And I have silver nitrate ions in it. Then essentially, if it's dissolved, then they are dissociated, right? By definition. So what I really have then, and I'm going to make this smaller so I can fit, is a lot of Ag ions and a lot of NO3 minus ions just running around completely separated from one another. Right? NO3 minus, not NO3 minus. Okay. Sarah's got a really good question. She says, if they are dissolved in water, how come it's not shown with water in the equation? And the answer is, well, two parts. First of all, the water is not reacting. So there'd be no reason to put it in the equation. But the other answer is that water is definitely shown in the equation, right? So the water is shown in the equation right here. The aqueous means, by definition, that means dissolved in water. So that just tells us that's where our reaction type is happening. And so you know that there's water present. Does that make sense? That's a great question. Okay. So we take, now we've got a little picture of this, right? So we're going to have, we have little ions running around in solution. We take this solution and we combine it with that solution, and we get a bigger beaker here. And what we find in our new combined solution is that my sodium and my nitrates are still running around, right? They're still aqueous. But my silver chloride is now a solid, and that's down here at the bottom. You can draw it as little solid pieces. We can point to it and say, this is AgCl solid. Does everybody understand that representation of what's going on here? Okay, so if we look at what's actually going on with the individual ions, we could, instead of expressing it this way in our complete molecular equation, it would be a better picture of what's going on, of what's actually present, if we did it, if we separated things out into their actual form, right? So what I really actually have is a silver plus ion that's aqueous, and a NO3 minus ion that is aqueous, and that's being combined with a sodium ion that's aqueous and a chloride ion that's aqueous. And that's going to form a silver chloride compound that is solid. And then what remains is we now still have a sodium ion that is aqueous and a nitrate ion that is aqueous. All right, what do you think of that? No, thank you. This is the complete ionic equation. Because it's complete because it includes everything that's present, and it's ionic because it's showing species as individual ions as opposed to molecules. Because that's how they actually exist, right? As individual ions. But I think Sarah's right. It looks messy, doesn't it? Looks more complicated, unnecessarily complicated. Sarah says, when I write it like this, how do I know that this silver is aqueous? And I'm just bringing this down. Good question. I'm just bringing it down from here, right? So since I have aqueous silver nitrate, then the silver is aqueous and the nitrate is aqueous, right? Because if it's aqueous, then it's dissolved. If it's dissolved, then it's dissociated. And so I know that each of these pieces is aqueous because they each came from here, as was seen in this bin. Does that make sense? That's correct. That's correct. Sarah says you can't tell that without the previous equation. So the complete ionic equation is a little bit misleading because it doesn't tell you where the silver is coming from. So it says that there's aqueous silver, but you know, knowing that silver is not always aqueous, you would kind of want to see what it came from. All right, well, we're not done. Should we? So why add another one? Well, the advantage to this is, again, to remind us that these aren't running around as molecules. Like, this is actually what's in solution, right? So this reminds us what's actually in solution, that it's not this molecule reacting with that molecule. It is these disassociated ions that are encountering each other and deciding that they're going to get off the aqueous boat and fall to the bottom there. Now, another reason to do this is as a little bit of a stepping stone to get to what we call the net ionic equation. And the net ionic equation is when you look at both sides and you say, you know what? Some of this stuff didn't actually react. I don't know why it's in my chemical reaction if it's not actually reacting, right? I've got sodium ions on each side. I have nitrate ions on each side. You can see it in the picture. You can see it here. We could almost treat this like a math problem and just subtract nitrate from each side, right? Canceled. Subtract sodium from each side. Canceled. Right? These are, all right, I won't cross them out. These are what we call spectator ions. They are present, but they are not engaging in the reaction. They are just watching. So we can condense this equation into something that's a little bit more manageable if we remove those and just say, look, I don't need to include them because they're the same on both sides. Just gonna shorten that there. Excuse me. And this is the net ionic equation. What's left over after I take out the spectators that aren't engaging. So this is telling us what is actually happening in this reaction. I have one solution that's providing a silver ion. I have another solution that's providing a chloride ion, and I'm getting silver chloride as the product. And this, how do you guys like this one? Is that simpler? Yeah, it's nice. It's very easy to see what's happening. Certainly easier than the complete ionic and even a little easier than the molecular. So these are kind of different ways to visualize what exactly is going on here, okay? And I need you to be able to do those. So let's look at our worksheet. We're at section 5, and we're gonna do exactly this with our stuff from section 5. We have 3 equations. I'm gonna give us some extra space here. We want to balance them and then, predict the products and then balance them and then write the net ionic equations. Now there's a little bit of a shortcut, by the way, let me show you, to the net ionic equation. And that is to say, you know the product of the net is the only thing that changed. The phase is different. You're at a solid here, so that's definitely part of my reaction. So I can put that as the product, and then I can say what gave me those 2 pieces. So this piece gave me the silver part. This piece gave me the chloride part. So these are the 3 parts that belong in my net. Ag plus Cl minus gives me the AgCl. You can kind of see that. All right, let's practice. All right, this is our more chemical reactions lecture. And right now we're looking at precipitation reactions and following solubility guidelines. Okay, so first thing, predict the products. How do I do that? Good. Sarah takes the outside ions, the cation from the first and the anion from the second. She notes that the cation NH4 has a charge of +1 and the anion NO3 has a charge of -1. And so she predicts that the formula, when she puts those 2 things together, is going to be just NH4NO3. And I'll drop those down. Perfect. And then Nicole and Sarah got this. Perfect. When we put these inside ions together, the chlorine with the lead, and you guys didn't articulate this, but you got the right answer, so I'm going to presume you noted that the chlorine has a charge of -1. The lead, we do not know the charge, except the fact that we know the charge on nitrate is -1, and there are 2 of them. That tells us the charge on lead is +2. So if the charge on lead is +2 and the charge on chlorine is -1, Nicole got it. We're going to need a formula of Pb with 2 chlorines to make that work. Everybody agree? All right. So we predicted the products based on the ion charges. Next, we need to balance it. How do I balance this guy? We've got 2 chlorine here, so we're going to need 2 chlorines here. So hang on a second, let me give me some space. I'm going to put a 2 right out in front, right there. Okay, that gives me 2 chlorines and 2 chlorines. Which makes it perfect, Nicole. So we need 2 NH4s on the right, so we're going to put a 2 right here. Excellent. And then that gives me 2 nitrates, which balances out the 2 nitrates that are already there. All right, perfect. You guys got it. All right. Oh, wait, we need to when we predict the products, we also need to include the phases here. So is the NH4NO3, is that soluble? Yes, so that gets a little AQ. All right, what about the PbCl2? Is that soluble or insoluble? That's solid. All right, we knew that ammonium nitrate was soluble because ammonium and nitrate both are polyatomic ions that are on the list of things which are always soluble, no exceptions. We know that the lead chloride is a solid because chlorides are generally soluble, but lead is a special exception to that rule. So whenever we put chlorine with lead 2, we're going to get a solid. Perfect. Okay, so we have predicted the products, including the phases. We balanced the equation. So now, what is the net ionic equation for that going to look like? All right, so I've got my aqueous lead. Plus my aqueous chloride going to form lead PbCl2, which is solid. Good, and I just left these so I could fill them in, and I just like to put them in the right place. All right. All right, so I've got lead 2 plus aqueous plus chloride minus aqueous goes to form lead 2 chloride, which is solid. That's my net. Does everybody agree with that? Good question. Sarah says, do you need charges in the net equation? For the ions that are dissociated, yes, because they are ions. If you didn't put a charge, then we would assume you were talking about elements. So you have to, if they are ions, you have to include a charge. Obviously, for the ionic compound, which is neutral, you don't put the charges in. All right, should we do another one? All right. What would you predict if I mix copper sulfate plus potassium hydroxide together? Good, we're going to mix the copper with the hydroxide outsides and the potassium with the sulfite. Uh-oh, guys, look at the charges. It looks super simple. Cu with the OH and the K with the SO3, but potassium's in group 1, so it has a charge of +1. Hydroxide is a polyatomic. You memorize as a charge of minus. Copper is a transition metal, so we don't know the charge, but we do know this one. The SO3 is a polyatomic ion sulfite, which has what charge? -2, perfect. And by the way, this is one of the reasons I ask you to memorize the polyatomic ions, because I need you to be able to do this quickly and not have to be referring to a chart on polyatomic ions while we're working on precipitation reactions, for instance. So because the charge on sulfite is -2, what is the charge on this copper? +2, perfect. All right, so now what are the formulas of the products that we are forming here? Perfect, perfect. So we're going to have 2 potassiums for every 1 sulfate, and we're going to have 2 hydroxides for every 1 copper, 2 potassiums, 2 hydroxides. Okay, that makes sense. Now that we have successfully predicted the products, we should also predict whether they will be soluble or not soluble. All right, good. Potassium sulfite will be soluble. Why? Potassium is always soluble. What about the copper hydroxide? Will it be soluble or not soluble? Solid. Why is that soluble? I mean, sorry, solid. That is insoluble. It's not on the table. Neither copper nor hydroxide are on the table of things that are soluble, so we can presume they're not. Now, Erica reminds us, we have to balance this. Okay, we're not done. We'll do it. We'll do it. How do we balance this equation? What do we do? Perfect. We're going to need 2 KOHs. All right. All right, so we predicted the products and including the phases as part of predicting the products. And then we balanced. So now we need to write the net ionic equation. What's that going to be? Sarah says it's going to start with the copper, with the 2+, aqueous. Okay. I'm going to add hydroxides. Each with a negative charge. So you wouldn't say OH2 minus 2, you would say 2 OHs, each with a minus charge, if that makes sense. Good. And that is going to form copper hydroxide to, let's say, solid. All right, how did you know that that was going to be your net ionic equation, Sarah? Perfect. Sarah says those are the things that reacted to form the solid. So when she said, okay, I need the net ionic equation, she says this is the solid, so that's my product, and the copper must have come from here, and the hydroxide must have come from here. So that's what's going to be included in my net ionic equation. Is everybody else with us? Sarah says, I feel medium confident in this. I feel medium confident in Sarah's medium confidence, but I'm not sure about everybody else. It's tricky. This is, yeah, no, it's totally fine. That's why I asked that. It is a little bit tricky. This brings together a lot of different pieces. It brings together our knowledge of how to form ionic compounds and kind of picking these apart and putting the cations with the anions and matching the charges. It brings together the balancing that we just barely learned, so that's still kind of new. It brings together applying our solubility rules, and then as a new part of it, it requires us to kind of conceptualize, to narrow that down to what's happening here and remove the spectator ions that are not being involved. So there's a lot that's here. Yeah. Okay, let's do another one. Let's do another one. Thank you for responding, Erica. I know that's hard on your phone. That's tricky. All right, let's do another one. So first things first, we're going to predict the products. What do we see? All right, Sarah says we've got NaCl. And what other product here? BaSO4. Okay. And Sarah noted already that we're going to need 2 NaCl's to balance that. Okay. So just as to remind us what we're doing here, we combine the outside ions here, the sodium and the chlorine, because the sodium is the cation from the first compound, and the chlorine is the anion from the second compound. Sodium has a charge of +1 because it's in group 1, and chloride has a charge of -1 because it's in group 7. So I know the formula itself will be NaCl. But as Sarah noted, in our original compound, sodium sulfate contains 2 sodium atoms, and barium chloride contains 2 of those chloride ions. And so I'm going to need a 2 in front of my NaCl to balance those out. Does that make sense, Alexander? Okay. And then we combine our inside ions, that is the anion sulfate from our first compound and the cation barium from our second compound. And we memorize that sulfate has a charge of -2 and barium's in group 2, so we know it has a charge of +2, so that's really convenient. We just need 1 of each and it just becomes barium sulfate, and that looks good. Okay, so now we did that, we balanced it. We do need to predict, phases, right? What's going to be solid, what's going to be aqueous. So is sodium chloride going to be soluble or insoluble? Oh, Nicole, perfect, soluble. So that's going to be AQ. That blue. Okay, what about the barium sulfate? Is that going to be soluble or insoluble? Insoluble, so that will be solid. Okay, so how did you guys know, again, that the sodium chloride was aqueous, but the barium sulfate was going to be solid? Yeah, sodium is listed. It's in group 1. It's the things that are always soluble with no exception. Good. And sulfates are generally soluble, but barium is a special exception to that. So those would not be soluble. Perfect. Excellent. So now we have done our equation. We've predicted the products. We balanced it. We've got our phases. So now we want the net ionic equation. Dun, dun, dun. Oh, Sarah's already got it here. She says, I take barium with the 2+ charge, which is aqueous. And I'm combining this with sulfate with the 2- charge, which is aqueous. Okay, hang on. Okay. All right. Is it okay if I say sulfate plus barium? Does it matter which one I put where? Yeah, it doesn't matter. It doesn't matter. If I put sulfate and then barium, that's kind of nice because the sodium sulfate was listed first and the barium chloride was listed second, but it really doesn't matter. It might be nice to leave it this way because then it reflects what was in my original molecular equation, but it's also totally fine to leave it this way because when we make our compound, the cation is always listed first, so that's also helpful. It doesn't really matter so long as we're including these 2 pieces, which are used to form my product here. Okay. Some good questions here. I'm getting to your questions. Zach says, are we starting backwards? And that's one way to do it. I find it to be one of the easiest ways to do it, right? To say, all right, this is the thing that changed, so it's gonna go right here, right? It changed as in we have aqueous, solid. So this is something new, it's gonna go right here. And then we say, well, what made that? And we pulled out the barium and we pulled out the sulfate and said, okay, that's what made it, and that's what gets included. That's one way to do it, yes. As Danielle says, doesn't the cation go first in our ionic compound? It does, but when I'm listing them, say this plus this, it doesn't matter if I say 2 plus 3 equals 5 or 3 plus 2 equals 5, it doesn't matter. Another way to do it, Zach, would be to look at the whole thing and say, what is the same, right? Here I have sodium chloride aqueous, here I have aqueous sodium, here I have aqueous chloride. So those all I can cancel out because I have aqueous sodium on both sides and aqueous chloride on both sides, and say, look, those are my spectators. Ions, well, hello. And then I can just eliminate those, and whatever's left over gives me my net ionic. Does that make sense to you guys? Whether you cancel the spectators or whether you just kind of look at the one thing that changed and then determine what was used to make that, both of those will get you the right answer. Okay. That's it for the first part of this lecture. We've got acids and bases coming up, but let's take a 5-minute break or so, and we'll come back and start working on that. All right, guys, we are back. All right. Just as a reminder, acid-base reactions also follow this exact same format where you have ionic compounds that split up like this. So it's going to give us a little bit of extra practice with this. But the difference is in an acid-base reaction, what happens is that an acid reacts with a base. Now, by definition, we should define this first. That we have an acid. This is a very simple definition. We'll do a more complicated definition in a little bit, but just to give us a little start, an acid is a solution with hydrogen plus ions, or a substance which adds hydrogen ions to solution. At a base is a solution with hydroxide ions, or that is any substance which is going to add hydroxide ions to a solution would be a base. Okay, so for instance, with some examples, if I had an AOH, I'm just going to toss a few things out here. You can tell me if these look like they're acids or bases. If I have HNO3, if I have H2SO4, if I have LiOH, and if I have HCl. Okay, so Sarah says that NaOH looks like it's going to be a base. Why does that one look like it's going to be a base? Because it has a hydroxide ion in it, right? And the HNO3 looks like it's going to be an acid because it has a hydrogen on it. Perfect. All right, what about H2SO4? Acid, same reason. Lithium hydroxide. Base, same reason. Okay, HCl. acid. Okay, great. All right, HCl is a little bit of an exception here. The rest of these, I hope you can look at and see they're ionic compounds. So they would split up in solution, and you'd get Na plus ions and hydroxide ions and H plus ions and nitrate ions, and so on and so forth. HCl looks like it's a covalent compound, and when it's by itself, it does act like a covalent compound, but if you put it in water, it acts like an ionic compound, and it splits up and forms H plus ions in solution. All right, so that's it gives you an idea of what acids and bases look like. Okay, so if I then put an acid and a base together, this is what that reaction looks like. Again, I'm following the same format. The AB plus CD goes to form AD plus CB. We also call this a neutralization reaction. And the reason for that is that you're neutralizing the acid with the base, or you're neutralizing the base with an acid. Acids and bases have kind of nasty properties, especially the strong ones. An acid is very caustic. It'll give you severe burns, and so will a base, right? So if you ever work in the emergency room, you might be unfortunate enough to experience, having a child come in who's drunk some Drano, and it just dissolves your esophagus all the way down, and then, of course, if you induce vomiting, it dissolves your esophagus all the way back up, and causes severe trauma, internal trauma. That's how nasty bases are, and drain cleaner is basically strong sodium hydroxide or a strong lithium hydroxide solution. If you've worked in the lab, you've probably seen acids like sulfuric acid and nitric acid and hydrochloric acid. Very strong acids cause chemical burns, cause staining, cause problems, will burn holes in your clothes. But if you put the two together, if you put a strong acid and a strong base together, then what happens is, of course, as we saw, the outside ions will interact and the inside ions will interact, right? And in this case, in any acid-base reaction, if I'm reacting an acid that's got an H plus with a base that's an OH minus, what I get is HOH, which is appropriately represented as H2O. So you take these things which have really kind of nasty properties, and you just make water, which is great. We don't worry about water, right? So you've neutralized that threat, right, in the formation of water. Again, you always have to watch, your H has a +1 charge, your hydroxide has a -1 charge, so you would need one of each. And then your sodium has a +1 charge, and the sulfate has a -2 charge, so you're going to need 2 sodiums for every 1 sulfate. And then when you go back to balance it, you'll say, I need 2 sodiums, so I need 2 of these. That gives me 2 of these oxygens, so I'm going to need 2 of those. That gives me 4 hydrogens, which is great because I've got 2 hydrogens there and I've got another 2 there, so now I'm balanced. Does that make sense to you guys? Good. And we can write these out as complete ionic equations exactly the same way that we did before. So we can say, all right, we have the H plus ion, which is aqueous, and I've got the sulfate SO4 2 minus ion, which is aqueous, and I've got the sodium plus ion, which is aqueous, and I've got the hydroxide ion, which is aqueous. Let me fill these in. Plus 4, 2 minus, plus, and a minus. All right, and then in our products on this side, that's a really good question, Sarah. Hang on a second, I'll get to it. On our opposite side, here we have sodium plus sulfate aqueous plus H2O liquid. Okay, so the question that Sarah asked is, she said, wait. Why is the water L for liquid? Doesn't it get to be AQ, because that means water? And the answer is no, AQ does not mean water. AQ means dissolved in water. So sodium can be dissolved in water, then I have a solution of sodium, right? And sulfate can be dissolved in water, because then I'd have a solution of sulfate. Water can't be dissolved in water, you just are water. So in a neutralization, acid-base neutralization equation, you'll have aqueous hydrogen, there's your acid, and aqueous hydroxide, there's your base, combining to make water, which is now listed as a liquid. It's not a precipitate, that's not a precipitation reaction, it's not a solid, right? And it's not aqueous because it's not dissolved in itself, it just is itself. But you do see the L because it's a liquid. Yeah, so you'll see it with water. That's right, Sarah. If it's anything that's not water and it's in water, then you'd call it aqueous. But if it's just water, it's a liquid. That's a really good question. I did not bring your attention to this, right? That in the product here, this is what has changed. Instead of forming a solid, I'm forming a liquid. Good question. Okay, so what are my spectator ions then? Oh, Erica's got a good question. How can you tell when something is going to be a gas? The answer is you kind of memorize gas forming equations. If it forms H2S or if it forms H2CO3, H2CO3, then it will be a gas forming reaction. That is beyond the scope of this class, so I'm not going to make you memorize those, but you just kind of get a sense for, okay, these are molecules which will become gases when they're formed. All right, Sarah, that's right. We have sodium on the left, sodium plus aqueous on the left and the right. So that is a spectator, and SO4 minus on the left and the right, so that is a spectator. So those are all spectator ions. All right, so if I eliminate the spectator ions, then what is left should be my net ionic equation. What's left if I eliminate my spectator ions? H plus OH minus goes to form H2O liquid. All right, plus minus H2O. That's it. That's my net ionic equation. Now, and we could balance it, right? 2 plus 2 makes 2. Don't really need, I mean, it's balanced as is, right? Because you would have 2 of each, and that would reduce down to 1. One fun thing to notice about acid and base reactions is that because the acid always has H pluses and the base always has OH minuses, and when they neutralize themselves, they always make water. This is always the neutralization reaction. This is always the net ionic equation for every acid-base reaction that we're going to see in this chapter. So unlike the precipitation reactions where you would have to say, oh, let me identify what the precipitate was, it always just makes water. And it's a little bit easier. All right, let's try it with another one before we look at our worksheet problems here. Going to play the same game, predict the products, identify the spectators, reduce it to the net ionic equation. So what are my products here, and how do you know? Oh, Sarah's got a good question. She says, I think she's talking about how originally you had two hydrogens and they reacted with two hydroxides, and we made, so in our original equation that was balanced, we had two of each. And don't I need two of each here in the net? And the answer is I don't need two of each here in the net. I can reduce that down to just one of each. So the most important thing is that you have, if you want it to be balanced, you just need the lowest whole number ratio that gets you there. And it doesn't have to necessarily correspond with the numbers that you had in the original equation. That's a good question. Okay, so for this one, we're going to combine the K, that's the cation from the first, with the nitrate, that's the anion from the second. And we note the potassium's in group 1, so it's got a +1 charge, and the nitrate is polyatomic, so it's got a -1 charge. There we go. And then we combine my inside ions, hydroxide with the hydrogen. And of course, you guys have memorized the hydroxide has a charge of -1 and the hydrogen has a charge of +1. That makes my life really easy, because then I can predict that I will form just KNO3 and HOH. All right. KNO3. All right. HOH is H2O, right? Gonna substitute that one in there just because it's a little easier to see, right? But they do mean the same thing. All right, what about phases for each of these? Good, this one's going to be a liquid because it's water. Water's liquid. What about KNO3? Aqueous, good. All right. Got this plus sign in the way. All right, so there's my, see, do I need to balance it or is it already balanced? It's okay, yeah, it's already balanced. I've got one of each potassium and nitrate, one of each. And then I have a total of 2 hydrogens and 1 oxygen in the reactant side and the same in the products. Okay, good. So then my net ionic equation, if I look at the one thing that changed, it was water here. So in my net ionic equation, that's going to be my product. I'm going to form water. And so what was used to form my water? Oh, you got it already. There was the hydroxide from the KOH. And again, I don't have to put them in this order. And then there was a hydrogen, but I will here, from the HNO3. So that's hydroxide, hydrogen, ion. It doesn't matter whether I say OH plus H plus or whether I say H plus OH minus. And look, our net ionic equation here is the same as it was for this other one. I told you they'd always be the same. Does that make sense? What are your spectators in this guy? Spectator ions. Yeah, the potassium and the nitrate. Those are all your spectators. I meant to do that green. Spectators. Okay, let's look at your worksheet. We've got just a few more to do here, just to make sure that we're understanding it all. Right, H2SO4 plus KOH. What are my products going to be? Yeah, the K is going to go with the SO4, and the H is going to go with the OH. Important thing to note here is that my H has a charge of +1. My sulfate has a charge of -2. Potassium is +1. Hydroxide is -1. So when I put these together, then, and this is probably one of the most common mistakes to make, right? It's just to put it together and be like, okay, I have one K and one SO4, so I must have KSO4. And that you'd be wrong. Because if sulfate is 2- and K is 1+, then I need K2SO4. Perfect, Nicole. All right, so put those together, that's what I get. What about the H and the OH? That's just gonna make H2O. Good. All right, and what are the phases here? Are these going to be solid, liquid, aqueous, gas, what? Aqueous for that one, and liquid for that one. Good, Sarah's got it. All right. So that is those are my products. Let's balance them. What do I have to do to balance these? Yeah, I need a 2 in front of the KOHs. Okay. It gives me 2 potassiums that will react with the sulfate. And then I'm going to need 2 for the H2Os. Good. Because I'm mixing 2 OHs with 2 H's. Okay. All right, I think we've got the products. We've got the phases. We've balanced it. Ooh, it says we need to identify the acid and the base. Which of these two things was the acid? Which was the base? Good, the H2SO4 was the acid because it provided the hydrogen. That makes the KOH the base, and that makes sense since it provided the hydroxide. Good. All right, and what is the net ionic equation going to look like? Yeah, guess what? Looks the same as every other acid-base reaction. H plus OH minus goes to form H2O. Good. Should we do another one, or do you guys feel like you got these? Okay, let's do another one. We have NaOH plus HNO3. Let's predict the products here. Good, this one's the base. Good, good, good. which makes this one the acid. Does that make sense that this one's going to be the acid? Excellent. Okay. And then when I combine the outer ions here, the inner ions here, helps for us to remember sodium has a charge of +1, hydroxide is -1, hydrogen is +1, nitrate is -1. So that's actually makes it really easy. Everything is 1 and 1. And so now we can just say, I put 1 sodium with 1 nitrate. Good. And then I add that to 1 hydrogen with 1 hydroxide, which makes HOH or H2O. Okay. All right. And this one, aqueous, and this one, liquid. Okay. Excellent, Sarah. Oops. There we go. All right. So we predicted the products by doing the outsides and the insides and following the charges. We identified our acids and bases. Do we need to balance it? Nope, it's already balanced. I mean, yes, we need to balance it, but we don't need to do anything to balance it. It's just done. All right, and what is the net ionic equation going to look like? Yeah, it's just going to be this hydroxide plus this hydrogen goes to form water. I can write it out, although it looks exactly like the ones we've done before, right? We have hydroxide, aqueous, plus hydrogen, aqueous. Uh-oh. Okay, I don't know why my keyboard stopped working in a minute. Okay, OH, aqueous, plus hydrogen, aqueous, goes to form H2O, liquid. Okay, so it's the OH minus, the H plus, and H2O. All right, that looks pretty good. I have confidence that you guys can do the last one that's here. We have just a few minutes and I'm going to jump backwards to section 2 of your worksheet here. Section 2 of your worksheet is a little bit of a review because it has you identify different types of reactions and just classify each of these as either oxidation, reduction, precipitation, or acid base. Now, when we first did this, you hadn't been introduced to any of those things. And I thought rather than giving you a very brief introduction and making you identify, I thought it might be better to identify them after we've really gone through them in detail. So let's see if you guys can help me identify which of these is which, okay? So for this guy, would you classify this as an oxidation reduction, a precipitation, or an acid base? Sarah says acid base. Why do you think that that's an acid base reaction? Yeah, you have liquid water as a product. Now that can't be the only reason that it's an acid base. To be an acid base reaction, you have to start with an acid and a base, right? So if we come back here, does it look like we have an acid and a base? We do, yeah. You see the OH in the calcium hydroxide and the H in the sulfuric acid, and those things together combined to make your water. So you did have an acid and you did have a base. Okay, that's you should double check. If there's water liquid as a product, that can be a good clue that it might be acid base, but you always have to identify the acid and the base that are combining together to make that. Good. Okay, what about this guy here? And if you want to skip it and come back to it, we can. Oxidation reduction, Sarah says. What do you guys think? I mean, you have liquid water, so would you call it acid base because you make liquid water? Sarah says no, we don't have an H and an OH, right? So it's definitely not acid base. Is this a precipitation reaction? Yeah, there's no solid forms. It can't be precipitation reaction. So if it has to be one of these, then by a process of elimination, it would be oxidation reduction. But let's put a couple question marks by that because we haven't verified like what gets oxidized and what gets reduced. We just know that it doesn't look like it could be anything else. All right, what about this third one here? Precipitation. Yeah, you see the solid formed. Put two aqueous solutions together so everything's dissolved nicely until they combine, and then all of a sudden, whoops, you've got a solid. Good. Okay, what about this one? Again, it doesn't really fit our rules for precipitation because there's no solid formed. And it doesn't really fit our rules for acid bases because you're not forming liquid water and it doesn't look like I have an acid or a base. So we can say again here, oxidation reduction. Okay. What about this guy here? Acid base. I do make liquid water. Here's my acid. You have the H plus ion. You know that it's combined with this polyatomic ion, so that makes it a nicely ionic compound forming with H plus ions. Ammonium hydroxide, there's your base. Beauty. Okay, what about this one? It looks like maybe oxidation. Guess what? This one is the same as this one. I don't know why I put it on there twice. It's on there twice. We'll come back to this one. We don't need to list it twice. Okay, what about this bottom one here? Precipitation. You've got that solid forming from two aqueous solutions. Okay, so these ones we labeled oxidation reduction mostly by process of elimination, but we should probably verify that something gets oxidized and something gets reduced for us to be sure to call that oxidation reduction. So this one, we've got covalent compounds, so we're going to follow those rules really fast. It won't hurt us to remind ourselves about those. So those rules say if it's covalent, you get to assign the hydrogen first, and then the oxygen gets what it gets, and it doesn't throw a fit. So since there's two hydrogens, each at +1, and two oxygens, then each of those oxygens must be -1. And then over here, again, we get to assign hydrogen first. Since there's two hydrogens, each at +1, that single hydrogen gets to be -2. And finally, all the way over here, my oxygen is 0. Does that look like an oxidation reduction reaction based on the assigned oxidation numbers? Yes, in fact, this one was from you do assign this in the oxidation reduction part of your worksheet. You can see that it's definitely oxidation reduction. Now this one is really tricky. So I would never assign it something as tricky as this one here. Now that's not so hard. There's no hydrogen, oxygen gets to be -2. If there's two of those, then the carbon has to be +4. Makes sense. Sorry, +1, -2. But then this is just kind of ridiculous. As a very rough guide, you could say, okay, if each of these gets to be +1, and each of those gets to be -2, that's +10. -4 gives you +6. So then each of these four carbon atoms on balance has to be -6. So it's like each of them is like -3/2. That's why I said it's really gross. It's not actually like this. You'd have to as a better thing, you would look at the actual structure and you'd see that some of those carbon atoms might be +3 and some of them might be -4, right? So it depends on the carbon atom, which one it is. But on balance, like that's where it kind of averages out. And as a result, is that 3/2? I don't even know. Anyways, as a result, hopefully you can see that yes, oxygen does change and yes, carbon does change. I don't have to know how much it changes. I just have to know that it does changes. It does change, and then that confirms that it's oxidation reduction. Okay, does this section make sense to you guys? You feel like if I gave you a reaction like this on the exam, you could predict what kind it was? Excellent. Okay, well then I will end there. This is the last part of our, I guess it's chapter 5. It's on chemical reactions, and we will jump in next Tuesday to math and chemical reactions. We're going to bring back dimensional analysis in a big way. So enjoy your weekend. If you can get a little bit ahead on the material, I think you'll find that it'll be worth your time. But have a great weekend, guys.